So, we're moving on to chapter 4 now, why things move. So consider the thought experiment of James Bond standing still in the middle of an ice-covered lake. The question is, if the surface and the bottoms of his shoes were perfectly slippery, with no stickiness at all, would he be able to move, or like run away or something? And think about that for a sec. The answer here is that no, you need an external force. So I'll just write that down here. You need an external, I would call it a net force in the horizontal direction is required. And actually, a lot of the times it's friction that gets you going. But if it's perfectly slippery, you don't get friction. So another way you could do it is, what if someone threw him a rope? So you can imagine that there's some environment over here. So there's like the system, and the book talks a lot about systems because it's good to draw this. This is the system. Is this guy. And then this is like the environment, something around. It is another person, actually. It's a whole other object. And then that person is applying a force. This is the force. And it's acting on the system. So it can accelerate that system. So the question is, what is a force? A force is like a push or a pull. You can see this person is about to throw the javelin by accelerating it or pushing it. We say that an external object exerts a force on the system. So from the system's perspective, it has a force exerted on it. And so you can also have a contact force, like you're actually physically pushing it. You can also have long-range forces, like with magnets, or even just gravity. If I just throw this, there is a force that's accelerating it towards the center of the Earth, so it's a long-range force. But if you play with magnets, you can get magnetism as a long-range force as well. And there's a units. So when I say SI, I'm talking about System International. It's meters, kilograms, and seconds for length and mass and time. Well, for force, the SI unit is called the Newton, named after Isaac Newton. So we're going to draw a lot of force vectors. Professor Kushner mentioned free body diagrams. I'm going to be talking about that a lot. When you draw a force vector, you can represent the object that the force is acting on as a dot, particle, and then you place the tail of the force vector at the dot, and then draw the force arrow pointing in the direction the force is applied, I guess, and then give it a label. And I like to remind myself that force is a vector by putting the little arrow over the F there. And from the book, you can see this is an example of somebody pushing a wagon. And there's a lot of forces going on here, but what they've done is there's a few things going on. First, there's what I would call like the sketch, the draw a diagram, and then there's the free body diagram, which is super important. And what that does is it takes a free body diagram of the boy plus the wagon. So the free body diagram always has to be of something. And so you usually draw a little dashed line. So it doesn't include like the ground, it doesn't include these pushers, okay? It just includes what's inside this dashed line here, although I put the ground in there a little bit. So it's pretty important to identify what all the forces are acting on. So all these forces, there's a normal force, there's a weight, there's a friction, there's F1 and F2 are from the two different people there. And then when you add them all up, all those vectors, you get what's called the net force. So the net force is the sum of all the force vectors, vector sum of all the force vectors. And you don't draw the net force on the free body diagram, you draw it sort of or you just compute it from the free body diagram. It's the combined effect of all the forces. Oh, we talked a little bit about Newton's first law of motion before, which is just that a body remains at rest, or if in motion, remains at motion at a constant velocity, unless acted on by a net external force. Moving right along, what is mass? So we're working up to Newton's second law, which is A is F over m. So we've got acceleration, we've been talking about that for weeks. I've just talked about force, so the mass is the next thing. Mass is a scalar quantity which describes an object's inertia. I was just saying that this bowling ball feels very massive. It's got a lot of inertia to it, so if I were to throw it at you out into the audience, it would destroy something, right? Because it wants to keep going at a constant velocity in a straight line. It's an intrinsic property of an object. It tells us something about the object. So it's related to how many neutrons and protons and electrons, I guess, are inside this ball. They all have mass, and altogether it adds up to some number of kilograms. And if we took it to the moon or to Mars or in deep space, it would still keep its same mass. And what goes on here, and we started doing this in practicals. I don't know if you've been to your practical yet this week, but there's this idea that the object has a mass. There's an external force on it, and that gives it acceleration. And I would think of the external force and the mass as kind of the causes of acceleration. What the net force does is the bigger the net force, the more the acceleration for the same mass. What the mass does is that the bigger the mass, the less the acceleration for the same net force. Oh yeah, this was a good one, although it's a little advanced. When you walk on the floor, is the force of the floor acting on your feet, the one that pushes you forward, is it friction? And if it is friction, is there another force that pushes backwards, that hampers your motion? So the two forces to be considered. So this is sort of chapter 5 stuff, but yeah, definitely, it's friction that pushes me forward, okay? When you walk. It's called static friction on the bottom of my shoes, and it's the main force that we would draw on a free body diagram if I'm accelerating towards the right. Now, it is true that there are also dissipative forces around, little small ones. There's going to be some drag from air resistance. Probably the soles of my shoes are a bit squishy, even the floor is a bit squishy, so I'm going to be generating heat as I'm walking, and all of that heat generated is going to suck away the kinetic energy I've got, so it's going to result in a little bit of a backward force, but we don't usually draw that on the free body diagram. It's a great question. Okay, now we're doing the bowling ball one. So we're going to observe a bowling ball, and one thing I'm going to do, situation 1, large initial velocity to the right, no pushing force. So this is after I launch it. There's going to be a small friction force from the floor that's acting opposite the velocity. So like that. Ugh. Okay. So what I would say here is the free body diagram of a bowling ball would just be, there's a normal force acting up, and there's a weight force acting down, and maybe a small little friction force acting backwards. So the net force is actually just that same small little friction force acting backwards, equals F net. Because what will happen is that the normal force and the weight will cancel in this situation because it doesn't accelerate up or down. It just accelerates a little bit to the left. So acceleration is like that. So next one, no initial velocity, pushing the force to the right from a meter stick. So I'm going to put an external pushing force like this to the right. And try to keep it steady. So the same amount of bending from the ruler as I go. And what happens is that it speeds up, speeds up, speeds up, speeds up. And you can kind of see that I'm applying an approximately constant force because of how much the meter stick is bending. So what it looks like there, again, it's the same normal force going up and the weight. Those cancel, so they don't matter so much. But now I've got this big force from the meter stick. So it looks like that, and I've got this more of an acceleration in this direction. This is the net force. And then the last one, we've got a large initial velocity to the right, and then the pushing force from the meter stick. So I think we have to switch places. I'm going to stand... Don't throw it too hard, but I'm going to try to slow it down with the meter stick with a constant force. And after John launches it. Okay, I actually slowed it down and then reversed it. So, all right, thank you very much. So the free body diagram there looks like, again, you've got the normal force, you've got the weight, good to draw that, and now we've got this force, F pushing backwards. So again, it looks like this. And bowling ball slows down pretty quickly and then eventually reverses velocity. So the acceleration is to the left there. So what's kind of interesting is that it's so massive. If we did that same force on, say, a tennis ball or something, it would have slowed down and stopped a lot faster. That mass not only does it make it hard for it to speed up, it actually makes it hard for it to slow down as well. Here's a list of forces that you might encounter in this course. There's the gravitational force, just sometimes called the weight. So sometimes I put a little lowercase w to be gravity force. Normal force I'm going to talk about, tension, kinetic friction and static friction, spring force, we've talked about that a little bit, and you can kind of think of it when you do the measurements of force in your lab. Drag force, this is actually going to come up in chapter 5, is we're going to talk a little bit about how to model air resistance and drag force. Electric and magnetic forces, these are more for sort of physics 132 concepts. Professor Harlick will be talking about in January. Thrust, so there's something like if there's a rocket or something that's shooting out fuel, and muscle forces, I guess, that's another force that comes up. So normal force, I'm going to do an example of normal force here, is if I'm standing on the table exerts a normal force on me. I can even measure it using this scale. It says, just make sure it settles out here. Oh my. It says, this thing it goes up every year. There's something wrong with it. It's drifting or something. So it's 201 pounds of force pushing upwards on me from the table. And by the way, if you look up normal in the dictionary, there's a lot of definitions. There's something about conforming to the standard. That's not what I'm talking about. Approximately average in psychological trait, free from mental disorder. No. Not talking about. I'm talking about the mathematical definition, which is being at right angles. So you have the table, and at right angles to the table, there's the normal force pushing up. So you got to imagine what would happen if the normal force disappeared. It wasn't there. Well, then I would just accelerate downwards. Like, I'd go into free fall because the gravity's acting on me all the time. And if you open up a trap door, I'm going to fall down and become a projectile. So normal force is all around us. It's exerted on all of us, and it's what keeps us still. It's also self-adjusting. That's the other interesting thing about it, is that if there was a lighter thing, like if I put the bowling ball on here, then less normal force is required to push it up. And that's just because it just sort of compresses until it comes into equilibrium. So I call it a self-adjusting force. There's no real equation for normal force. It's just whatever it takes to keep the situation in the acceleration that you're given. This is a picture of me water skiing in Idaho near my mom's place, but there's a rope there. It's pulling me along. So whenever you have string or rope, and we're going to be doing a lot of this next week in practicals, the tension force exists, and it pulls sort of on both ends of the rope. And there's gravity. You'd say that if you have this tennis ball or an angry bird or something that's flying through the air, then the Earth exerts a gravity force, and it's called W. It's mg. So G here, it's kind of interesting. I sometimes think of it as 9.8 newtons per kilogram. So you may have remembered that gravity is 9.8 meters per second squared, is the acceleration due to gravity. Well, I will tell you that in SI units, meters per second squared and newtons per kilogram are the same unit. But this way I think of it is that this is an equation which gives you the force of gravity. So you've got now something's mass, and now you multiply it by 9.8 newtons for every kilogram, and that gives you what this external force of gravity is on the object. And then it also depends on your position. It always pulls you towards the center of the Earth. So if you're in Australia, gravity acts in the opposite direction. Everyone just flies upwards from this. Well, no, because the ground's on the opposite side there too. So they're all stuck upside down on the opposite side of the Earth, which seems hard to believe, but let's do an example. Let's do this wagon, mass of 50 kilograms, and you pull it to the right with a rope with a tension force of 10 newtons. So let's draw a sketch here. So I'm not going to draw a free body diagram right away. I'm going to draw what I like to call a sketch, which is just to try to get my head around what the heck is happening here. So there's a wagon. It's got 50 kilograms of mass, and there's a tension force, T is equal to 100 newtons, and it's pulling at an angle of 30 degrees above the horizontal, equals 30 degrees. And it says the wagon accelerates to the right, so that's okay. We're going to define here plus y is up, plus x is to the right. Question A, what is the normal force of the floor on the wagon? So find N. And then B is going to be, assume that there's no friction forces acting backward on the wagon. What is its acceleration? So find A. So next I'm going to draw the free body diagram of the wagon. So whenever you draw a free body diagram, it's always of something. You have to pick an object. Sometimes if there's more than one object, this is a bit tricky. So let's do the wagon. So what you do is you draw a dot, and then you draw all the forces acting on that object that you can think of. So you just try to think. Maybe people could shout out, any force, what's acting on the wagon? Shout a force. Weight, that's a good one. That's a good one to start with. Everything has a weight if it's near the earth, so let's draw that down like this. What else is acting on the wagon? Normal, yeah, that's good. Normal, so that's going to act up like this. Normal. Anything else? Friction we're not going to draw because there's no friction. I'm going to put somewhere here that there's no friction. But that's a good one. If there was friction, it would be acting opposite the velocity. We're not going to show that. Anything else? Tension, that's right. Okay, and I think that's it. So the tension acts up like this. And I put little arrows on them to remind me that they're all vectors. This is y and this is x. And you can, whatever way you want to go with this, but what I like to do is I would say let's make a table. Let's make a list of the forces, the x component, and the y component. Because you can add components just like they're numbers, right, scalars. So the forces, and let's just list them here, there's the normal force. The x component of the normal force is 0. The y component of the normal force is just n. I don't know what it is, so I'm just giving it a letter. I'm calling it n. It's going to be something. We're going to find it by doing the net force. Then there's the tension. So unfortunately, tension has got the diagonal, so I'm going to draw a little right-angled triangle. If the tension looks like this is T sub y, and this is T sub x, and this is theta. So that the sine of theta is the opposite divided by the hypotenuse, and the cosine of theta is the adjacent divided by the hypotenuse. And so all of this information tells me that the x component of the tension is going to be T times cosine theta, and the y component of the tension is going to be T times sine theta. And then the other force is W, and that's going to be 0 and negative mg. And then we can just add them all up, add the columns down, and get F net. F net x is just going to be T cos theta. F net y is just going to be normal plus T sine theta minus mg. So you shift to the right, to the left, and then the acceleration is to the right. They just tell you that in the thing. I guess it probably can't accelerate up or down. So this means a sub x is 0, and a sub y is equal to the a. So you use Newton's second law of motion, which is that a sub y is equal to F net sub y divided by the mass is equal to 0. So what this means is that the F net sub y is equal to 0. And that was, you can get it from over here, n plus t sine theta minus mg. And you can, I think question A is solve for n. So you get that n is equal to mg minus t sine theta, 50 times 9.8 minus 100 times sine of 30 degrees is equal to 440 newtons. So that's your normal force. And they mention in the book that you use n for normal force and n for the newtons, so that's kind of sad. And then a sub x is F net x divided by m. And that's going to be t cosine theta divided by m. So it's going to be 100 times cosine 30 divided by 50. So I got the acceleration is 1.73 meters per second squared. So it was really crucial, I think, for me to draw the free body diagram so that then I could find all the components and so I could solve things. There was just no way to look at this wagon and figure out what the normal force was on it. How would you ever guess that the normal force is mg minus t sine theta? I don't think you would guess that. So rather than guessing, you kind of have to step through these things. And so somebody asked, do I have to draw a free body diagram in the test? The reason that I require it is because I think it's kind of critical to draw it in order to sort out all these forces in your head and solve the thing. We are going to talk about Newton's third law, which is whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. There's an old fable, which is that a farmer has a donkey, And every morning, the donkey pulls this wagon from the shed to the field. But then the donkey begins taking Physics 131. And the donkey's not here right now. He's doing the asynchronous section, so watching the video in the future. One morning, the donkey refuses to pull the wagon, and the farmer asks, "What's wrong?" And the donkey replies, "Professor Harlow said that according to Newton's third law, if I exert a forward force on the wagon will exert an equal magnitude force backwards on me, so I can never accelerate the wagon." So the question I'm going to talk about on Friday is, what is the flaw in the donkey's reasoning there? So this is Newton's third law. Forces always come in pairs. So a force is an interaction. And it always involves two objects and two forces that are always equal in magnitude and opposite in direction. There is no isolated forces in nature. They don't exist. So that's what we call a force an interaction. Okay, it's between two objects. So when you have like an interaction pair of forces, which you always have, they are always, not only are they equal in magnitude, opposite in direction, they're always the same kind of force. So if it's normal, they're both normal. If they're gravity, they're both gravity. If it's tension, they're both tension. And they always act upon different objects. Okay? And it's usually, sort of towards the middle or out, right? Like a pull kind of force or a push kind of force. Okay, so let's do an example here. A truck is pushing a car up an incline with a constant forward acceleration. So there's some angle theta with respect to the horizontal. The car and the truck remain in contact during this acceleration. And in this situation, as in all situations, Newton's third law is true. So I guess what I'm thinking here is that the car died on the hill. So they ran out of gas or something, and so there was a truck, and someone waved them down and said, "Hey, can you help push me to the top of this hill? Because I know there's a gas station up there." So the guy actually touched the car with his truck and is now pushing the car, and they're accelerating up the hill and towards the gas station. If you can imagine that. Let's see where my notes are here. Yeah. Okay. The force of the truck on the car is equal to the force of the car on the truck. And one way that I would think of that, if you think of a spring that's between the truck and the car, like maybe this spring right here, the spring might have some negligible mass compared to the truck or the car. Maybe it compresses, maybe I guess to protect the bumper of the car or something, they put a spring there, right? But the spring, in my opinion, doesn't know which side is the car side and which side is the truck side. It's sort of symmetric, right? It's just pushing. Or pulling, I guess. But in both cases, I feel like the spring, just sort of being a symmetric object, can't kind of distinguish between its left and right end. That's one way I try to wrap my head around this. So how does it really work? Let's draw the free body diagrams of the truck and the car. So let's call the truck, just to keep track of everything, I'll call that T, and we'll call the car C. So I'm going to do the free body diagram of truck, FBD of the truck here. So there's the truck, and then we're going to do the FBD of the car. So anytime you draw a free body diagram, you have to pick an object. So, truck. Let's see what the forces are here. Well, there's going to be the weight of the truck. Let's see, like the weight of the truck. Okay. There's also going to be a guess weight of the car, right? Probably a little less weight of the car. Then there's going to be the normal force. Well, it's always a little on an angle here. So I'd say there's going to be this normal, I guess, on the truck, and then normal on the car. Okay. What else is there going to be? There might be some little friction force, I guess. Okay, so what's weird is that the truck's got its engine on, so there's this forward friction force on the truck. That's what's pushing it forward. And then there's probably the car doesn't have its engine on, so it's got a little backwards friction force on the car. But then I'm going to change to a different color here. What's going on here, and the reason the car goes forward, is that there's this forward, I don't know, like a normal force of the truck on the car. And then there's an equal and opposite normal force of the car on the truck. And so Newton's third law says that the normal force of the car on the truck is equal to negative the normal force of the truck on the car. And maybe what I didn't do there is show that the static friction force of the ground on the truck is much bigger than that backwards force of the car on the truck. And that's what keeps this whole system going. So this is what is called, I guess, an interaction pair. So whenever you have two different free body diagrams for different objects and they have a force on each other, you can find the interaction pair and set those forces equal and opposite. He doesn't want to pull the wagon because he feels like if he pulls the wagon forward, the wagon will pull backwards on him with an equal and opposite force, so what's the point? So what is the flaw here? So what I think is going on here is that the first sentence, Professor Harless says that according to Newton's third law, if I exert a forward force on the wagon will exert an equal magnitude force backwards on me. That is correct. That's how these interactions work. The second sentence, so I can never accelerate the wagon, is not correct. So, forces cannot cancel out if they're acting on different objects. We're assuming here that it is possible for the forward static friction on the donkey's feet to be larger than whatever backward friction is acting on the cart. That's why the cart has wheels. You can see it's got these big wheels on it. So that's to reduce the friction on the cart and make sure that the friction on the donkey's feet is greater. That's the only reason that the donkey can actually pull the cart, is because friction on his feet is bigger. So let's think about some more interaction pairs. So people wonder, how do you drive the car? Well, you push the gas and you go, right? So what's happening? You got to break this down. First thing that happens when you step on the gas is that there's a torque on, in this case, it's the back wheels, which is going to rotate the back wheels counterclockwise. And what that's going to do is it's going to push backward on the road with some static friction force. And then, by Newton's third law, the ground will push forward on those back wheels with static friction. And it is static friction which pushes your car forwards. And if you don't believe me, wait until winter and it's really icy and step on the gas. You're not going anywhere because your wheels will spin, but there's not enough friction to get you going. You'll be stuck. So it's the earth, I guess, or the ground is pushing forward on the tires of the car. So it's Newton's third law that solves you that. So this also happens with rockets. They can even fly around in deep space without the earth being near there. What happens is that the rockets will push the exhaust, all that gas that's the fire that's going out there, that has mass, and you're pushing against that. Well, that exhaust is pushing forward on the rocket, and that's how you can accelerate. And this is the only way we know how to accelerate if you're out in space. There's no such thing as warp drive for Star Trek fans. You need to actually have propellant and exhaust that goes the opposite direction of which way you want to go if you're in space. This morning's pre-class survey, there were all these forces on an elevator, and I think so there was tension in the rope that's suspending the elevator. There's the normal force on the bottom of the scale. There's F, P, and F. The force of the scale on the bottom of the elevator, the weight of the elevator, the weight of the scale, the weight of the person. Which are the forces, of the forces listed below, which act on the person? So I think it's just the W, the weight of the person, and the upward force of the scale on the person's feet. All the rest of those forces are acting on something else. So if I was going to draw a free body diagram of the person, I would just put two forces on it. I would just put it like that. F, S, and W. And the net force would give the acceleration of that person. And that's the nice thing, right? Is that acceleration is equal to F net divided by the mass of the person, I guess, right? If this is of that person. So if we define plus y is up, then you would say that the acceleration of the person is Fs minus the weight divided by the mass of the person. So if the spring scale is reading higher, then the weight means you're accelerating upwards. If it's reading lower in your weight, you're accelerating downwards. And I don't know if you've ever stood in an elevator and actually felt that. My kids love it. They jump. They press down and they're like, whoa! They feel a little lighter. And if you were standing on a scale, you would be a little lighter as you're just as you're descending. And you feel a little heavier just as you're accelerating upwards. We got a little time. Let's do an example. And this is also something you're going to do next week where you've got a hanging mass and a cart. So the cart has mass m, and then you have a hanging mass. So what you've got here is two connected objects. And you're going to use Newton's third law to connect them. So you've got the cart of mass m, and you'll have a free body diagram for that. So I'll just do a quick sketch of it. It looks kind of like that. And you've got some tension pulling upwards on it. And then you've got the hanging mass with the tension pulling up on it. Hanging mass m, lowercase m. And I will say that since they're connected, the acceleration magnitude is going to be the same for both of them. And so basically, if the hanging mass moves like 1 centimeter down, the cart will move 1 centimeter up the ramp in the same amount of time. And so it'll have the same displacement, it'll also have the same velocity, and it'll have the same acceleration as well. Same for both objects, because they are connected by a string, and the string doesn't change its length by a string. Sort of conservation of string length or something. So what we're going to do is do free body diagrams. We're going to do the cart. So it looks like this. You've got the normal force kind of acting at an angle. You've got the tension force acting like that. They're going to be perpendicular to each other, and you're going to have this angle theta between the tension force and the horizontal. And then acting straight down, you've got the weight, which is the force of gravity, which is m times g. I'm going to call the force of gravity F sub g, just to kind of remind myself what it is. I don't really like the term weight very much. Force of gravity. And I'm going to define, for the cart, I'm going to define x to be up the hill and y to be tilted like that. And the thing that's, so if I do this definition, I'm also going to assume no friction on the cart. It's a pretty low friction cart. So the diagonal force, if you tilt your axes like this, is actually the m times g. So if you've got the force of gravity acting straight down, then I think this is negative the force of gravity in the y component, and this is going to be negative the force of gravity x component. And this is a right angle triangle. I'm doing these components, and what I think is that it's kind of hard to do here, but if this is theta, then this angle right here is 90 minus theta. And so this angle, let's go to red here, is going to be 90 minus 90 minus theta, which is theta, I think. So it's hard to find these angles, but I think this is theta up here. And so what that means is that sine of theta is negative fg x over fg, and cosine of theta is negative fg y over fg. So there's a little bit of triangle work that you have to do to split up the components of that cart and its gravity, but that's what I did with the free body diagram there. We need a free body diagram for the hanging mass. So let's do hanging mass. You've got the tension going up now, and the force of gravity on the mass, which is lowercase m times g, going down. And what I'm going to do here is I'm going to define plus x is down. And the reason I want to do that is because I defined the plus x of the cart is going up that hill, and if it goes up that hill, the mass will go down by that same amount. And I guess opposite, if the mass goes up, then the cart is going back in the negative x. So this will match up the x's a little better. So the acceleration in the plus x direction to make these the same. So, and what I'm going to do is say that this way, A is the same for the mass, the hanging mass, and the cart. So now we can just set this up. The cart, the net force in the y direction is n minus fg y equals n minus capital M times g times cosine theta. And the f net in the x direction is just going to be the tension minus fgx. So it's going to be tension minus m times g sine theta. And we know that there's no y acceleration of the cart. It's balanced in the y direction because it's staying on the track. That's why we tilted the axis. So that means that f net in the y direction for the cart is equal to 0. and that's equal to n minus mg cos theta. So the normal force equals mg times cos theta for the cart. And then the acceleration is F net x divided by the mass of the cart, and that's tension, minus mg sine theta divided by capital M. And I'll call that equation 1. And then for the hanging mass, use its free body diagram. You don't have to worry about the y there, there's just x. You've got a sub x, same a sub x is F net on the hanging mass in the x direction divided by lowercase m. And that's going to be its mg pulling down minus the tension pulling up, because we defined plus x to be down, divided by lowercase m. And we can call that like equation 2. So basically we have two equations and two unknowns. So we can solve for them. You've got acceleration in the x direction and the tension. And we need this acceleration, that's what we've been asked for. And we don't care about the tension, so we're going to eliminate tension somehow. So what I like to do is I solve for tension, the thing we don't care about, in both equations, or in one of the equations, and then plug it into the other, and that'll eliminate it. So let's solve for tension in equation 1, and then plug it into the other one. So I would say that we'll use 1 to solve for t. You got acceleration is equal to t minus mg sine theta divided by capital M. Mass times acceleration equals t minus m times g times sine theta. T is equal to m times a plus g sine theta. What we're going to do is plug this into 2. Plug into equation 2. So acceleration is mg minus capital M times a plus g sine theta, all divided by m. But the problem is you have to solve for a. You end up with a is equal to g times lowercase m minus capital M sine theta divided by m plus m. So I'll kind of leave it at that. The idea here being, you can check sort of the limits here a bit. If you know little m is much, much bigger than the mass of the cart, then this is sort of negligible on the top. The big M is, if it was 0, for example, you get m over m here, and you'd be the acceleration is just 9.8. It would just fall. And similarly, if the hanging mass was 0, you would end up with the cart going backwards with g sine theta, which is exactly true as well. Someone said, can you explain again the top hat question from our last class? So I'm still confused about how the spring works. So what's interesting here is that all three of these answers seem to make some sense. If you look at just how much weight is being supported, 100 plus 100 is 200 newtons. Also, if you look at the net force on that spring scale, well, there's 100 newtons pulling it to the left, and then there's 100 newtons pulling it to the right. So the net force in the spring scale is 0. And then I've also said it's 100. So which is it? So it's 100. So let's actually go through a little bit of a thought experiment. There's 3 slides I'm going to go through here. So the first one is, let's say I own a spring scale, and I hang it from the ceiling, as spring scales should be hung, and hang 100 Newton mass off of it. So meaning 100 newtons means that the weight of that mass is 100 newtons. What do you think it should read? So whoever designed the spring scale, the manufacturer made it read 100 because that's what it's supposed to do, right? Otherwise, you've calibrated your spring scale wrong. So that's actually how they find the little lines on the spring scale. It stretches some amount. They balance it out so that if it's 100 newtons, it reads 100 newtons. Now, all I want to do is instead of the ceiling, I want to tilt it around a pulley. And the property of pulleys is that if a string is wrapped around it, and it's an ideal massless, frictionless pulley, like a very light thing that spins very easily, then the tension is the same on both sides of the pulley. It just changes its direction. So we haven't changed much. All we've done is just change this perpendicular. So what I would like to think here is that it should just still read 100 newtons. It's just like as if it was hung from the ceiling, but it's hung from a wall. And now, I'm going to replace the wall with another pulley. Wall, pulley, wall, pulley. Okay, so what I'm saying here is that how does the spring scale that's right here know if the thing to its right is a wall or if it's just another 100 Newton mass that bounces off hanging off another pulley? It can't know. This is the unknown territory over here. It could be a wall, it could be something, but the point is, it's still 100 newtons. 100 over here, 100 over here, and that's what it reads right there. A string is attached to the rearview mirror of a car. A ball is hanging from the other end of the string. The car is accelerating to the left. You measure that the angle that the ball hangs is theta relative to vertically down. What is the acceleration of the car? So you can use this as an accelerometer to find out how fast you're accelerating. So what you do is you define, I will define plus y to be up and x to be to the left, so that ax is positive by this definition, and a sub y is equal to 0. And so what you've got in this force diagram, again, you've got mg down, you've got tension up there. So tension is a diagonal, T is, so every time you have a diagonal force, you're going to have to break it down into its x and y components. So I think this is Tx, and this is Ty, this is T. And I think that if you look at this as being the y direction and use kind of the z rule or something, if you've ever done the z rule, then I think if those are two parallel lines, there should be a theta right down here as well. So sine of theta, there's the right angle, is opposite over the hypotenuse. And so T sub x is equal to T sine theta. And the cosine of theta is T sub y divided by T. So T sub y is T times cos theta. And so then you just do Newton's second law. F net, say in the y direction, is going to be T sub y minus mg. So it's going to be T cos theta minus mg, and that equals 0 because a sub y is equal to 0. So a sub y equals 0 implies that T cos theta equals mg. So you get the tension is mg divided by cos theta. And then you can do F net in the x direction is equal to, I think it's just T sine theta, right? And A sub x is equal to F net in the x direction divided by the mass. And so it's going to be T sine theta divided by m. We've got T from the y thing, so we're going to plug in. And you've got the A sub x is equal to mg times sine theta divided by m times cos theta. The m's cancel, and you get a sub x is equal to g times sine theta divided by cosine theta. So if you can measure theta, and you know g, you can actually figure out how fast your car is accelerating. And at no point do I involve the drag of air resistance, because there's no motion through the wind, because the windows of your car are rolled up. Let's talk a little bit about ropes and pulleys. Basically, the tension in a taut string or rope is some number, T. I usually make T a positive sort of number, scalar number. And if we can neglect the mass of the string compared to other objects in the problem, then each end of the string pulls with the same force. It's called the massless string approximation. You don't need any net force to kind of make the string accelerate around, because it's small mass compared to the masses of the other things. And then if the string is wrapped over an ideal pulley, a frictionless, massless pulley, then the string has the same tension on both sides of the pulley. What is the acceleration? We can actually solve for the tension and the acceleration if we just work through this. So what I would do is, once again, let's draw a free body diagram of, let's say, MA. That's the way you've got to start all these problems. You've got the normal force acting up. You've got the weight of A acting down. You've got the tension acting towards the right. you've got the acceleration, which is going towards the right. We're going to define here, let's do y axis up, x to the right, so that a sub y is equal to 0. It's not accelerating up or down. And also a sub x is going to be f net x divided by the mass ma. Because this is the free body diagram of ma. So when we do the Newton's second law for that object, we take all the net force divided by the mass of that object. That's why it's really important to keep track of what object you're drawing this free body diagram for. And so what do you have here? Well, I guess just F net in the y direction is equal to n minus ma times g is equal to 0. But F net in the x direction, and that's important, is equal to t. So that a sub x is equal to F net x divided by ma. It's equal to t divided by ma. It's about as far as I can go with the free body diagram of A. Then we have to draw the free body diagram of B. If you don't draw these, I don't really know how you can solve any of these problems. You can't just sort of guess your way through this. You have to sketch it. So what do you have? There's B. Well, you've got tension going up, and you've got its weight going down, WB, which is going to be M sub B times G. Well, that's it. And what I'm going to do here, this is my little trick, is I'm going to, I know that the acceleration here is down, it's falling, so I'm going to define plus x is down for this. And so I'm going to put a note over here because it's kind of important. We choose plus x to be to the right for A and down for B, so that, the reason I did that, I want A sub x equals to A sub x for both. Because the string is kind of connected, right? So I know that as this thing moves to the left, let's say the thing goes up. If this thing moves to the right, this thing goes down. So they're kind of connected by this string. So I know that their velocities will be the same, or the speeds, I guess, and their accelerations the same, but just tilted by that. Something to do with conservation of string length. What was I doing? Yeah, I was just doing that F net in the x direction is equal to mb times g minus t. Remembering I've defined positive down, so the weight's a positive number here, and tension is negative. So a sub x is equal to F net in the x direction. There's Newton's second law. And this time we divide by the mass b, because it's the free body diagram of mass b. Just equals mb times g minus t, all divided by mb. So what I'm going to do is call this equation 1, call this equation 2. Then we have two equations and two unknowns. And we can solve for ax and t. So that the unknowns are ax and the tension. And so we can solve for both if we want to. But you're actually only asked for the acceleration. So equation 1 implies that the tension is equal to ma times its acceleration. We're going to plug this into 2. So ax is equal to mb times g minus the tension, which is ma times a sub x, divided by mb. And we're going to have to solve this for a sub x. So I don't know if you've noticed, but there's a sub x on both sides of this equation. So it's not clear what a sub x is. So what you have to do is isolate a sub x on one side of the equation, divide everything, and try to get a sub x equals a whole bunch of stuff that doesn't have a sub x on the right-hand side. mb times a sub x equals mb times g minus ma times a sub x. Now I'm going to add ma times a sub x to both sides of the equation, so I get mb times a sub x plus ma times a sub x equals mb times g. So the trick there was, now I've got all the a sub x's on the left-hand side, so I can now pull out a factor of a sub x, and I can say that mb plus ma all times a sub x is equal to mb times g, and then I've got it. Now I've just got numbers that I know on the right-hand side, and I've got things that the thing I'm trying to find on the left-hand side, and so we're done the problem. All we have to do is plug in the numbers that we were given. 3.5 plus 13.2. So I got 2.05 meters per second squared. And it's, by the way, this is positive, so the hanging mass is 2.05 meters per second squared, and I would say it's down. Accelerates downwards. And that's kind of exactly what happens if I take this thing and just let it go. It accelerates downwards as the whole thing slides over. The other thing I wanted to do is just kind of a sanity check here, is I wanted to do, why don't we actually solve for tension? So also, from equation 1, the tension equals ma times a sub x. And we have a sub x now, so it's just going to be ma times mb times g divided by the total mass. So that's kind of interesting. Is that less? What we could do is actually calculate it. It's 27 newtons, if you work it all out. And the weight of mb is, WB is just equal to 3.5 kilograms times 9.8. It's equal to 34 newtons. So again, the tension is less than the weight. Okay, so you've got this exact same setup that you're going to be doing today or this week sometime in practicals. And instead of letting it accelerate, what we try to do is set up an equilibrium problem I want to show you. So you have an angle measurement device, and the idea that you want to do, you hang this thing. You're going to hang the 50-gram mass, and then the problem is it always wants to accelerate downwards. But what you could do is tilt this up. Just so if you tilt it up too much, the mass accelerates up. If you tilt it not enough, the mass accelerates down. So you want to find this ideal angle where there's no more acceleration. See how that looks. If I push it up, it sort of slows down and stops. If I push it down, it keeps going down. Maybe I'll lower it just a tiny bit more. So this is equilibrium. So somehow the gravity is canceled out on this cart. Whatever component of gravity is just enough to support this mass. So this is the situation that you're going to set up in practicals. And so let's call it a FBD, free body diagram, of lowercase m. So what that'll have is the tension up, and it's little lowercase m times g acting down. And I can put plus x as down. And then I can do the free body diagram of capital M. And that looks like this. You've got the normal force acting that way. You've got capital M times G acting down like that. And you've got the tension acting up at an angle like that. I can remember that these are vectors. And what I'm going to do, if this is plus x, I'm going to I'm going to tilt my axes so that y is up and that plus x is along that track going up like that. So that again, this acceleration, if it's that way, makes this one go down. I just wanted to match those up. So what this means is that gravity is the diagonal force. So what you have to do, unfortunately, is try to split this up, theta. Then I think this is 90 minus theta. And so this is theta down here. So what I've drawn here is this is mg. This is negative of the, it's the weight in the x direction, I guess. And this is negative the weight in the y direction. And I think what we're going to do is we're just going to say that the acceleration is 0. So this means that the tension equals mg. And then similarly here, F net in the x direction for m, capital M, is going to be, if this is a right angle here, then I think actually the gravity is pulling in the negative x direction. And so what we should do here is say that sine theta is equal to the opposite, negative wx, over mg. So the wx is negative mg sine theta. Similarly, cosine theta is negative wy divided by mg, so that wy is negative mg cos theta. Anyway, F net x is just the x component of the weight plus the tension. So it's going to be the tension minus mg sine theta, and that equals 0. So I would just say that the tension here is equal to mg sine theta. So tension equals tension over the pulley, and lowercase m times g is equal to capital M times g times sine theta. Divide g by both sides, and you get sine theta is equal to little m divided by capital M. So theta is equal to sine to the minus 1 of little m divided by capital M. I want to talk about the fundamental interactions in physics. So there's 4 of them. There's gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And so gravity, obviously, it's a super long-range force. Even right now, the sun is orbiting around the center of the Milky Way galaxy, which is 50,000 light years away. But when you are living on near a big object, like a 6 times 10 to the 24 kilogram object like the Earth, then the dominant gravity force you're always going to feel, even though it pulls all objects towards each other, is going to be towards the center of that planet. So that's how we experience gravity. So what are we made of? It's just a little review here. We're made of atoms. Atoms are too small to be seen by visible light, but if you have a scanning tunneling microscope, you can actually map out the atoms that are on the surface of, like, graphite, I think, here. 1 little cubic centimeter of water has about 10 to the 23 atoms in it, so they're extremely small. Those are little carbon atoms in those dots, actually. But what an atom is composed of, so in the subatomic structure here, is there's a nucleus, which contains protons and neutrons, and there's orbiting electrons. And these are the electrons, is what you learn about in chemistry. But in nuclear physics, you learn about the protons and the neutrons, which they themselves are made up of smaller quarks. Protons have electric charge of +1. Electrons have charge of -1, electric charge. And neutral atoms have the same number of protons and electrons so that they cancel out. And neutrons are neutral. So the electromagnetism force, basically in Physics 132, you're going to learn about the electric force and the magnetic force as being different forces, but it's possible, using special relativity, to unite these 2 forces. So we have unified electromagnetism into one thing called the electromagnetic force. But in 132, you'll treat them as different forces. One is like static electricity, and one is like actual magnets. But this is actually what's responsible for normal force, tension force, spring force, friction. So this was from today's Precast survey. The answer to, of the 4 basic forces of nature, which one is responsible for the normal force? It is the electromagnetic force. So 50% of you got that correct. It's not gravity, actually. Gravity is that long-range force that pulls things towards the center of the Earth. And the strong and weak interactions, they don't really come up in this course because they're very short-range forces. They don't extend beyond sort of the nucleus. So the weak interaction is what's responsible for beta decay, when a neutron can turn into a proton and also an anti-electron and an electron and an anti-neutrino. And then the strong force is what actually holds all the nucleons together. So all the neutrons and protons are attracted to one another by the strong nuclear force, and that's what prevents nuclei from just exploding due to electrostatic repulsion. You've got 3 blocks are being accelerated upward at 3.2 meters per second squared by a force that is applied to the bottom block. So they're being pushed upwards. The mass of the bottom block is 7 kilograms. The mass of the middle block is 14 kilograms, and the top block is 21 kilograms. So this capital M has a value which is 7, I guess, and you got M, 2M, and 3M. So, and the question is, find the magnitude of F. So what I'm going to do, since they're going up, I'm going to define plus Y is up. And I'm going to, I think what I'll do is define the system here equals all 3 blocks. And I know that A sub Y is equal to plus 3.2 meters per second squared. And I know that the mass of the system is equal to 7 plus 14 plus 21, so it's 42 kilograms. And what we need is F, that pushing force. So the free body diagram of the system is just, looks like this. You've got the F acting up, and the M system times G, the total gravity force acting down. And what I'll just note here is that internal forces do not go on the free body diagram. When you draw a free body diagram, what you're doing is you're picking your system. It could be multiple objects, but once you've drawn your little dashed line around it, you now draw all the external forces from outside, from the environment that are acting on that. And all it is just gravity and this pushing force from below. So we'll just use that A sub y is F net in the y direction divided by the mass of the system. So it's just equal to F minus M system times G divided by M system. And you solve for F. You get F is equal to M system times A sub y plus M system times G. So it's a little bit more. So you get 42 times 3.2 plus 42 times 9.8. And you get 546 newtons. Okay. And then the next question is, what is the magnitude of the normal force that the top block exerts on the middle block? So the way I would do that, let's just see if I can find it here, is I would define now this system to be this top block. So if, let's actually set 1 is the top block, 2 is the middle block, and 3 is the bottom block. Why don't we define the system just to be the top block here equals 1. If it's just that top block, then what we need is the normal force of 1 on 2. But by Newton's third law, the normal force of 1 on 2 equals, I guess, absolute value of the normal force of 2 on 1. And so what I'm going to find is, let's find this one, the normal force of 2 on 1. A little easier to do. So if I draw the free body diagram for my system now, I've got the normal force of 2 on 1, and I've got the mass 1 times g. So that's the free body diagram for my system. There's only 2 external forces on it. And so once again, A sub y, the whole thing's accelerating upwards, F net y divided by m1 in this case. So it's going to be m1 times A sub y is equal to the net force, which is n2 on 1 minus m1 times g. And you can solve it out. N2 on 1 is equal to m1 times A sub y plus g. So you get 21 times 9.8 plus 3.2. So it equals 270 newtons. And that's, I would say, the N1 on 2 is the same thing, 270 newtons by Newton's third law. So the trick here is when you get these questions, you can experiment around with defining your system in different ways.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.